Okay. Okay, so do you hear me and see my screen?
Yes, we do.
Yes.
Great. So, 1 moment. Okay, so the talk is about symplectic duality and Hikita-Nakajima conjecture for ADHM varieties, and it is based.
Just one remark. When I saw the title, I first read it as Nikita-Nakajima.
Oh, yeah, this is Hikita, Japanese mathematician.
It's not Nebraska.
Вась, и так теперь в вашем окошке почему-то виден планшет вместо вас.
Ну да, вот так тогда.
Ага, вот так лучше.
Okay, Hikita conjecture for ADHM spaces, joined with Vasily Krylov. Let's start from the general class of varieties that we will be considering. They are called conical symplectic resolutions. So like informally, conical symplectic resolution is the following data. We have a affine Poisson in general singular variety Y, and the certain resolution of this variety by some variety X that is already smooth and symplectic. And also we have an action of one-dimensional torus C times on both of these varieties. This action commutes with our morphism, which is known by pi, with our resolution of singularity. And this action contracts variety Y to one point. That's why this is called conical symplectic resolution, because we have a conical action of C times on Y.
Just a second, contracts all Y.
Yes, contracts all Y.
So not just singular point of Y.
Yes, so this point to which it contracts Y will be a singular point of Y. We will see an example. Let's discuss an example. So the first example, maybe the simplest one, is T star P1, which resolves the nilpotent cone inside SLN. So what is that I denote by N? What is N? N is the space of nilpotent matrices inside SLN, SL2, sorry, SL2. And about this contracting action, the action just scales a matrix, so just multiplies it by T. So every matrix contracts to just a zero matrix in this example. And let us describe N in this particular case. So N is the space of nilpotent matrices of the form A, B, C minus A, since they lie in SL2. Nilpotence in this case is equivalent to the fact that this matrix has zero determinant, which in particular means that our space N is just the space of triples A, B, and C, such that A squared plus BC is equal to 0, like a cone with centered at 0. And what about the resolution? What about T star P1? It's not hard to show that T star to P1 can be identified with the following pairs: line inside C2 and nilpotent element A inside our N, which maps line to 0 and maps the whole space C2 into this line L. And our resolution just forgets the line L. So this is the basic example. Any questions about this example? Okay, let's now discuss example number 2, which is a certain generalization of this example, but still rather explicit. So instead of considering T star to P1, we can consider T star to Pn minus 1. And for our X, for a smooth variety. And then Y, I denoted by On, will be the following space. This is the space of matrices inside SLN, such that rank of this matrix is less than equal than 1, and the square is 0. So in particular, these matrices are still nilpotent. In the same fashion as previously, T star to Pn minus 1 will be pairs of a line now inside Cn and a matrix inside SLN, which maps L to 0 and maps the whole space inside this L. So this is the example number 2. Some people know it as like a resolution of closure of minimal nilpotent orbit inside SLN. Any questions?
ON is a closure of the minimal.
Exactly. ON is a closure of the
orbit.
Yes, coadjoint orbit. Minimal non-zero. Yes.
And this A is from SLN or from ON?
It is automatically from ON. Note that this condition implies that A square is equal to 0 and rank A is less than 1.
Very good. Thank you.
In the definition, you also had symplectic form on one side and Poisson structure on another side.
Yes, great. So the symplectic form here is the standard symplectic form on T star to Pn minus 1 as a cotangent space. And the Poisson structure here comes from the Kirillov constant Poisson bracket on SLN star. So this variety is subvariety inside SLN, and we just restrict, it's a Poisson subvariety, and we restrict standard form from SLN to it. Okay, let me then discuss example number 3, which is also, which is also rather simple. So this example is the following. Consider the group Z mod NZ acting on the two-dimensional affine space in the following way. The generator 1 of Z of NZ acts on XY by, let me write it again because, oh yeah, now it's clear. Sorry, something, one moment. Let me try to, yeah, now it's okay. So the action is the following. It multiplies x by e to the power 2pi divided by n and multiplies 1 to the power minus 2pi divided by n. These are primitive roots of order n. And then our affine and Poisson space Y will be A2 modular this finite group gamma. Explicitly what it is, if you consider functions on this quotient, then by the definition, they are invariant functions on A2 with respect to this group. And so these are just functions C of xy, xn, yn, which can be described as just C of A, B, C with one relation, A to the power n minus BC. So this quotient is the following variety, known as type A resolution, type A singularity, I believe. So this is our y, and our x will be a certain resolution of this variety. So it's known that this variety can be resolved by n-1 blow-ups, and this will be our x. Yes, any questions about this example? Okay, great. And let's now discuss the example number 4, which will be actually the most important for us from the first point of view. And from the second point of view, it will contain all the previous examples as a particular cases. So example number 4 will be about Hilbert scheme of endpoints on A2, or more generally, the ADHM space, which I denote by M and R, or even more generally, quiver varieties M of Q, which I will discuss only a little bit. So let me define this space, because this is the main player of our talk. We fix positive numbers N and R, and we denote by V the vector space C to the power N, and by W the vector space C to the power R. And let us consider the following space, which I denote by M or M and R, which will be homomorphisms from V to V to the power 2, plus homomorphisms from W to V, plus homomorphism from V to W. So you can think about this space as about the representation of the following quiver. And here X and Y are these homomorphisms from V to V. So as you see here, they act from V to V, here and here. And also we have gamma and delta, and gamma goes from W to V and delta from V to W. Any question about this definition? Okay, so we have this space, just a vector space, and on this vector space, we have an action of the group GLV, just changing the basis. This action is actually symplectic, and we have a moment map, mu, which can be described as follows. You just map your quadruple, x, y, gamma, delta, to the commutator of x and y plus gamma delta. This is just some map from M to GLV, a very natural one. And let me also give one definition. So quadruple x, y, gamma, and delta is called stable. Yes.
Excuse me, is it gamma delta or delta gamma?
I think gamma delta, because you want an element of GLV. Yes, so you go from
gamma delta is in W. If you want to,
you go from V to W, and then from W to
sorry, it's I read it in. Okay,
yes, yeah, that should be fine. Okay, yeah. So now definition: our quadruple is called stable if for any vector subspace S inside V, which is preserved by Y and X, and such that the image of gamma lies inside this S, we must have S to be the whole V. So in other words, like the image of gamma, when we act on it by X and Y, we get the whole V. Okay, and now we are ready to give the definition of the ADHM space. So, yeah. So we have this moment map, we have this notion of stability, and then M and R, ADHM space, is defined as the pre-image of 0, stable part of it, modular GLV. And the corresponding affine variety M0 and R is defined as just the pre-image of 0 modular GLV. And the claim is that the natural map from X, M and R to Y, M0 and R, is exactly the conical symplectic resolution. Singularities.
But I'm sorry, the lower line is not visible.
Oh, sorry.
Thanks.
Yeah, so here is our main player. So this guy is Y, this guy is X. And I will discuss later some examples when it can be described more explicitly than as such a quotient. But so far we have this definition. Okay, great. And let me just mention that actually this construction using Hamiltonian reduction can be very, very naturally deformed as follows. We can consider M universal version of M and R and the corresponding universal version of M0 and R.
I'm sorry, still the same problem.
Oh, sorry.
Jenny,
I see the
actually it
bottom
is
line.
visible, but you have to like remove your cursor from the panel down the screen.
Doesn't work in my case, but
Okay, I'll try to
For me, it is visible. Was
do
visible.
my best.
Remove and wait till it's disappeared.
It's also visible for me, Женя, but while we're discussing technical issue, Vas, and do you have this file somehow, since it's already written, can you send it to the chat?
Yeah, may I send it to Misha? And I thought I forgot, I also have a PDF notes of this talk in 2 versions.
Just because some
You can send everything to me and I send to the chat.
Yes, 1 minute. 1 minute. And these PDFs.
I got it.
And also these PDF files. They are more. There are more details there. Okay, so can I continue?
Well, is it
Yes,
question to Женя or to
Okay, so returning to our picture, so we have these guys, and we can also consider certain deformations of them, which are defined as follows. Now we're taking pre-image with respect to mu, not of 0, but of the center of the GLV. Since it commutes with all GLV, everything works fine. So these are just certain one-parametric deformations of our original spaces, which will be important for us later. Okay, and let's now try to give some more explicit description of these spaces when R is equal to 1. So this is the case R equal to 1.
Vanya, say it again. Z of V is center of
our group GLV, to which a moment map goes.
Center of group?
Oh, sorry, algebra. Sorry.
Algebra. Okay.
Apologize. Yeah.
Diagonal matrices, like
just diagonal matrices. Yes.
Like constant.
Constant diagonal matrices. Yes. Let me write it. So Z of V just diagonal. Z times. Okay, great. Yeah, so we can consider the following space, which I denote by Sn of A2. By the definition, this is the quotient of A2 to the power n by the action of the symmetric group Sn. How you can think about this? This is just the variety that parameterizes unordered n tuples of points of on A2. So you have just n points of A2, and then you forget the ordering. And this variety is singular when n is greater than 1 and Poisson. And actually, this variety has a symplectic resolution, which is the so-called Hilbert scheme of n points on A2. And the definition is the following. This is the space of ideals inside C of xy, such that the dimension of the quotient is equal to n. And this variety is already smooth and symplectic. Okay, and the claim is that for R equal to 1, our space Mn1 is nothing else but just a Hilbert scheme of n points on A2. And the corresponding M0 and 1 is just Sn of A2. So it has rather explicit description. And let me say one word about this isomorphism. Just my point is just that it's rather simple. It does the following. You start from your ideal J of codimension n, and then you produce the quiver data as follows. Your V will be the quotient of C of xy by this G. Operator x will correspond to the operator by the multiplication by x on this quotient. Operator y is the multiplication by y on this quotient. Delta will be just 0, and gamma will send 1 to 1 here. Okay, any quotient or any questions about this isomorphism? Yeah, sorry, about overlay file, I think that, Misha, you should open it if just a minute slower and just send the PDF to others. Sorry. Okay.
Maybe I sent wrong link, just I will fix it.
Okay, thank you. Great. So we have this description. And then let me recall that also we have this M0 and 1 universal deformation. And we already know that our original M0 and 1 is Sn of A2. Natural question, how to describe M0 and 1 universal in these terms? Yes, using some similar descriptions. And the answer is the following. So let me recall that functions on Sn of A2, what is it? These are just functions on A to the power 2n invariant with respect to the group Sn. So this is just functions depending on variables x1, y1, ... xn, yn. And then we take invariance with respect to the group Sn. One way to think about this algebra as about a center of the following semi-direct product. You can consider group algebra of Sn and consider the semi-direct product of it with these functions C of x1, xn, and y1, yn. Then the invariants are just the center of this algebra. Why it is useful to think in this way? Because this semi-direct product already has a very natural one-parametric deformation, which is called rational Cheritenic algebra HN, and I will define it in a minute. Are there any questions about this slide? Okay, let me then define this rational Cheritenic algebra. So Hn is a quotient of the semi-direct product of C of Sn and C of x1 of xn, y1, yn. The difference now is, you see, brackets are like angle, right angle. So these variables do not compute now. And we take a tensor product with C of kappa. Kappa is just a formal variable, our parameter of our deformation. And the relations are the following. X's and Y's, X's compute with X's, Y's compute with Y's. And the commutator of Xi with Yj, when I is not equal to J, is equal to minus kappa times Ij, where Ij is just a permutation, transposition. And the commutator of xy and yi is equal to kappa times the sum of all transpositions of the form ij. J is not equal to I. You see that, yes. if you put kappa equal to 0, you will just get that x's and y's commute. And this is a certain non-commutative deformation. Okay, and let me state then the theorem, which is due to Cheritenic and Ginzburg, that these universal deformations, functions on it, is nothing else but the center Zn of this rational Cheritenic algebra. So you can think about it also in this way if you use this one parametric deformation. Any questions so far? Okay, great. So let me now return to the general picture. So what about general R? So for
in what sense this is a natural identification? So what's so non-commutative about the this Nakajima space?
Nakajima space is totally commutative, and that's why we're considering center here.
Right. But why is it natural to identify the space of functions on some variety with
actually,
the center of some algebra?
Actually, so this in the same way as in representation theory of Lie algebras, you know that the symmetric algebra of G can be deformed to the universal developing algebra, which is already non-commutative. In this picture, you can there is also quantizations of these functions on M0 universal N1, which are non-commutative. And at this side, you will get rational Cheritenic algebra, which has additional parameter here, like H bar or T. So you can also put T here, and this algebra will have a very small center, but it will be still true if you consider the symmetrization of this algebra with respect to the trivial idempotent in the group algebra of symmetric group, then this symmetrization will be isomorphic to the quantization of this guy. So in some sense, these varieties, they have something non-commutative inside them, since they have very nice theory of quantizations of them.
Vasily, do you mean that quantization is spherical?
Yes, quantization is spherical subalgebra inside a rational Cheritenic algebra.
But what's the but how can I see the full Cheritenic algebra?
So see the full Cheritenic algebra. So you need to do more. Let me not. I believe that then you should consider these Procesi bundles and something like this. So something n factorial of dimension n factorial over the base. Okay, great. So, okay, what about the general R? For R equal to 1, we had our M0 N1. We had this rational Cheritenic algebra for Sn, and we had Sn of A2, which is this quotient, and this was the same as this. In general, this M0 and R1 becomes M0 and R. There is also a candidate for the rational Cheritenic algebra depending on R. Exactly, we should do the following. We can consider rational Cheritenic algebra, but now corresponding to the following group. We consider the semi-direct product of Sn with Z mod Rz to the power n. This is still the group generated by reflections, and the work on symplectic reflection algebras of Cheritenic works very well for them. So this is the natural candidate. But this candidate, if you restrict to, so this candidate, it deforms what? It deforms the following thing. It deforms A2 to the power n modular by this semi-direct product. So this is whom becomes this Sn of A2. And actually we have seen something like this, so you can think about this space as a byproduct of our two examples. One example is Sn of A2, symplectic resolution, and another is this A2 modulo Z mod RZ. And this is certain generalization of both of them. Okay, but what is the point? The point is that now for arbitrary R, these two spaces are not isomorphic. This is true only for R equal to 1, these Poisson varieties. That's why I denote one by Y and another by Y shrink. But what is true, that they are symplectically dual. And I will
Can you
discuss
repeat again how to come to the spaces?
Yes, so one space is just this M0 and R that we define. Yes.
Okay.
And another one is the following. So we discussed that for R equal to 1, M0 and 1 can be identified with Sn of A2.
Mm-hmm.
And this identification and the universal deformation comes from the center inside the rational Cheritenic algebra for Sn.
Mm.
And now for general R, you want to invent something similar. So you want to replace rational Cheritenic algebra for Sn by some rational Cheritenic algebra for some different group, which will depend on R. And the natural candidate is the following group. I mean, this is arguable that, that you should consider this group exactly. And then if you consider rational Cheritenic algebra for this group, then it will deform this quotient. You just take the same A2 to the power n as we have taken previously. And now bond out it not by Sn, but by this semi-direct product.
But isn't it just the symmetric, the n-symmetric power of the AR minus 1 singularity?
No. You have semi-direct product here, so it's more. So. Yes, you're absolutely right. Yes, this is just Sn of yes, that's true. Because you can take invariance in 2 steps. Yes, that's a very good comment. Maybe now it becomes more natural to think about this. Yes, thank you very much. So now you add singularity inside your surface.
Just to follow, so you have defined the Hilbert scheme of endpoints on C2, and then you have two ways to include additional integer number R. One way is to consider not shifts of rank 1, but shifts of rank R, and another way is to take the quotient by the discrete group. And
Exactly.
you denote these two parameters by the same letter R, and you say that the result will be dual.
Yes. In some sense, yes. Let me return back. Yeah, so I'm saying that these varieties are symplectically dual. And let me explain, just try to explain what it means. Okay, so symplectic duality. Let us recall to the general situation. So we have X mapping to Y, we have this contracting C times. And let's consider the group of automorphisms of Y which commute with this C times, and which preserve Poisson structure. And let Sy be a maximal torus inside this group. And let small si be the Lie algebra of this group, Sy. And let Ty be the second cohomology of X with coefficients in C. So these are 2 vector spaces which we can attach to our resolution, Sy and Ty. It turns out that this space Ty has the following meaning. This is the base of a certain universal deformation of our varieties. So there exists variety X universal mapping to Y universal, which both live over this space Ty, and such that the fiber over 0 of these maps is our original map from X to Y. And we have already seen these universal deformations for quiver varieties. Okay, so this is the general.
In that case, this cohomology is one-dimensional, and this corresponds to parameter, which is a value of the central element in the algebra.
Exactly. Exactly. Roma.
So you've got like Y is also deforming, right?
Yes.
Okay,
and in our case,
now.
M0 and R also deformed. Yes, so you can take.
So if we take point 0 with T1, then on this point, the preimages will be just X and Y. And for generic point.
Yes.
In example before, for a generic point, we have a map from X to Y will be isomorphism.
Exactly. This will be, so in the case that we're considering, so yeah, let's say that this will be always true. If we're considering good symplectic resolution, then this is always true that this map is isomorphism generically. Okay, great. So now it turns out that, or it's predicted by physicists and mathematicians that symplectic, so that if we have some symplectic resolution x, y, then there should be a symplectic dual resolution x shriek to y shriek. And for now, let me just say that one like basic prediction of this symplectic duality is that these spaces, so the space Ty on the left-hand side should be isomorphic to the space Sy shriek on the right-hand side. And the space Sy on the left-hand side should be isomorphic to the space Ty shriek on the right-hand side. This is not the definition, since there is no definition of symplectic duality. This is just one of the first simplest prediction. The goal of my talk will be to discuss another prediction, which is much more unexpected, maybe, and for me at least. This is the so-called Hikita-Nakajima conjecture. This is also a prediction of symplectic duality. But in order to do this, let us first of all discuss our main example. So our main example is Y is M0 and R, and Y shriek is this quotient, it's Sn of the A R-1 singularity. And then what about the universal deformations? So on the left-hand side, the universal deformation is just this M0 universal and R that we discussed. On the right-hand side, the universal deformation is the spectrum of the center of this rational Cheritenic algebra H and R, which that I defined only for R equal to 1, but the definition is in general is similar. And so the torus which acts on the left-hand side, Sy, I denoted by S, this is just C times to the power R. And this C times to the power R, it acts, let me briefly say. So we have a natural action of PGL of W on this M0 and R. And we can consider C times to the power R-1 here. And also we have an action of additional C times, which does the following. It multiplies X by T y by t inverse and doesn't change gamma and delta. And our torus S, let me also write it here, is the product of these two actions, of these two torus. So altogether we get c times to the power r. And finally, this sy shriek is just c times, which just acts on A2 where t inverse.
I see. Probably you can't do anything with that, but you have x and y's, which are matrices and which are the varieties, right? So,
A moment.
so I mean, in the formula for the action of t.
Yes, yes, that's true. Yes, I'm sorry, but yeah, I believe this my conventions. Yeah, I'm sorry about that. Okay, and so what we see, you see that this space is formation is one-dimensional, and this torus is one-dimensional. This torus is r-dimensional, and this rational Cheritenic algebra is an r-dimensional deformation. And for this, maybe for the specialists, it's r-dimensional because the space of parameters depends on the number of conjugacy classes of reflections in our group. And since our group is Sn semidirect Z mod Rz to the power n, there are exactly r conjugacy classes. One for transposition in Sn and r minus one here from this side. So we get r parametric deformation. Any questions about this example?
The word reflection means the transformation which have invariance of space of codimension 1.
Yes, exactly. Exactly.
That means square is equal to 1.
Exactly. And yeah, so for example, here, like the generator and Z mod RZ will be a reflection, but it will not have order 2. Okay. Just to say about our previous examples, so T star to P R minus 1 resolving or R will be symplectically dual to a resolution of AR singularity. So Hilbert scheme will be symplectically dual to itself. And this is why we had this description of M0 and 1 as Sn of A2. This is a consequence of self-duality. And the cases about which I didn't talk, so equivariety should be symplectically dual to the corresponding column branch. Let me just put it here. Okay, great. And let's now discuss this equivariant Hikita-Nakajima conjecture. So first of all, let me introduce some, let me give some definition. Let Y be an affine variety with an action of C times. Consider the corresponding algebra of functions.
So just to follow, so in your previous, when you say as examples, am I right? The two of them are just particular cases of your main example, and third.
Exactly. And then the main example is a particular case of the third one.
Yes, and main example is particular case of the third one. I see.
Yes, exactly. And I'm putting this last line here because if I'll have time, I'll make some conjectures about this general situation. Okay, so equivariant Hikita-Nakajima conjecture. We have variety, we have functions on it, and the action of C times induces us the grading on these functions. B is graded by integer numbers. And let me then define what I know by Y C times. These are so-called schematic fixed points. By the definition, schematic fixed points is a scheme functions on which are the quotient of B by all the elements Fi which have degree not equal to 0. Okay. Let me give an example of what is this thing. Example number 1. Let's assume that y is just a1, and we act by c times just by multiplication by t. So t times y. Then the corresponding b is just c of y, and the degree of this y is equal to 1. So schematic fixed points will be what? We take b of y, c of y, and mod out by all powers of y greater than 0.
Vasily,
So
can you raise a little bit screen?
Yeah.
No, just up. I don't see the last, the last line.
The other direction.
Wait,
Yeah.
sorry.
Okay.
Sorry. Yeah. So this yc times will be just spectrum of c of y modulo the ideal generated by y. So this is just the spectrum of c. So this is just the point 0 fixed point with respect to our action inside A1 with no interesting scheme structure, just 1 point. This is example number 1. Any questions about this example? Let me show the definition. Okay, now example number 2, which is more interesting. Let us consider our space N, which we like, which is an important cone, A, B, C, A square equal to BC. And we consider the action of C times, which doesn't change A, multiplies B by T, and multiplies C by T inverse. This is like the conjugation action. 2 by 2 matrices. Then, as a set, these fixed points, this is just 1 point, yes, 0, 0, 0. Because if you have fixed point, B and C must be 0. And then from this relation, you conclude that A should also be 0. But what about this definition? Our definition of schematic fixed points tells us that functions on this space should be functions on N mod out by B and C. Yes, these are 2 generators which have non-negative degree. And so we get C of A, B, C and mod them out by B, C and A square minus BC. And then B and C cancel out, and they cancel out then A square. So we get C of A modulo A square. But this is not C. So we get something interesting. We get not just like complex numbers as functions on 1 point, but we have complex numbers and we have additional nilpotent element A, which lives here. Any questions about this example? Okay, and then let me make one remark. So actually, when y is smooth, then the fixed points are also smooth. So there's no interesting scheme structure on these fixed points, and you can consider them just as ordinary variety. And interesting things happen exactly when y is singular. And we have already seen this in our 2 examples. So in first example, we had something smooth and we just got 1 point. And in the second example, we had something non-singular and non-singular precisely at this point 0, 0, 0, 0. And we got something interesting. Okay, let me now formulate the Hikita-Nakajima conjecture. So we have x to y, one resolution, and we have the symplectically dual one, x shriek to y shriek. And we have an action of sy here on y, and it rises to x. And we have on this side, we have this universal deformation of x shriek universal mapping to y shriek universal, which lives over ty shriek, which by symplectic duality should be equal to sy. So here Sy is a torus, and here Sy is a parameter of our deformation. And let us also fix some generic co-character of the torus Sy shriek. Then the Hikita-Nakajima conjecture says that the equivariant cohomology of X with respect to this torus Sy is isomorphic to the algebra of schematic fixed points of the universal deformation with respect to generic co-character. Let me stop here for a minute just to look at this conjecture, because it's very unexpected. Yes, on the left hand, for me at least. So on the left hand side, you have something purely topological. So this is just, so if you erase the Sy, this will be just ordinary cohomology, algebra of cohomologies of X. And on the right hand side, you have something purely algebraic, which depends only on this Y shriek, and something defined, yes, pure algebra. And the claim that these algebras are isomorphic. Note that both of these algebras are algebras over functions on the algebra of this Sy. Any questions about this conjecture?
Is there some simple reason why these two algebras should be related by any means?
So I think that this is the question to physicists. So I mean that I will, so soon I'll try to explain you how to prove this conjecture for the ADHM space, and then you will see that, like, I mean, proof is rather natural, so you can track it and see why they are indeed related. But I don't have any good explanation of this conjecture in general.
And in what cases the conjecture is known to hold?
Yes, so it is. Let me.
I don't think physicists formulated this conjecture even remotely. I don't think. I mean, I think this is one of the statements. I mean, I think I don't think the with this conjecture at all. It's just it was found sort of experimentally, I think.
Mm-hmm. I see. So there is no physical reason.
Not that I know of, and no, I don't think so.
Okay, so let me say then, when this conjecture is known, I'll try not to forget some situations. So let me say this briefly. So this conjecture is known when X is the Springer T star G mod B resolving the nilpotent cone, and it's due to Hikita. So no, I'm not really okay. To be more careful, so why I'm calling this conjecture Hikita-Nakajima? This is because Hikita's original conjecture was a not deformed version of this one. So Hikita original conjecture was that just cohomologies of X, this algebra, is isomorphic to the schematic fixed points of Y shriek nu of C type. And Hikita proved this version for T star G mod B for Hilbert scheme of points on C2. Yes, and also conjecture is known for equivarieties of type A in this generality. M of Q when Q is type A. Equivar. Yes, and also Pavel Shlikov proved this conjecture in, I believe, in these four resolutions of for ADE resolutions. Okay, so there are some cases when this conjecture is known, but certainly not so much of them.
Isn't it a statement about the structure of the beta roots of the kind of quantum integral system, which is based on X?
Yeah, maybe we will see this at the very end of the talk. Yes, maybe this is.
In that case, I tend to disagree with Braverman's statement.
Okay, great.
But I'm not sure. I'm not sure that. I mean, you might be right, but actually, I don't see why it's the same statement.
Yeah, I don't.
You need to you compactify the 3D theory on the circle, and you study the.
No. The question is why what you said about beta roots and so on. Why does it imply this? I don't see that.
Yeah, maybe let's discuss it at the very end.
See, in some sense, this work, for example, of Openkov and Kanadjic, when they talk about quantum K theory of these varieties and so on, but and which is supposed to be kind of a much more general statement than this. But again, I don't know how to formally deduce this statement from what they say, because somehow,
well, because they're not physicists. So because they're not physicists, so it's a statement about the structure of the vacua of this theory.
Right, but this is like a thing, because there everything depends on some parameters, and somehow all the statements are when values of parameters are generic, and this would correspond to some very non-generic values of the parameters. So you have to be careful about how things degenerate. So you might be right, but somehow I don't see how to do it carefully.
Okay, thank you very much. Yeah, so let me continue. Okay, so the main theorem of this talk is that, recall that we have this symplectically dual pair. X is M and R, ADHM space, and Y shriek is this quotient, which is deformed by the spectrum of the center of rational Cheritenic algebra. And the theorem is that Hikita-Nakajima conjecture holds in this situation. In other words, that we have an isomorphism between cohomology, equivariant cohomology of M and R with respect to the torus S, and schematic fixed points of the spectrum of the center of the rational Cheritenic algebra. Any questions about the statement?
If you're talking about duality, you should expect two such isomorphisms.
Yes, that's true. So we yes, and our theorem is about starting from M and R, and yeah, so M and R on the left and Y shriek on the right. Okay, so let me now try to give you the idea of the proof.
Vasy, I'm sorry, do you have an explicit description of the algebras?
So
for
yes, I do. So there is a description if it's explicit. So I mean, so for example, you can describe them as the center of the corresponding cyclotomic Hikita algebra. This is rather explicit. So we have rather explicit generators and relations. And for R equal to 1, you can do this even more explicitly. Actually, these algebras, so not deformed one, will be the associated gradient of the center of the group algebra of the symmetric group, as associated gradient with respect to filtration when you put transposition in degree 1. And the generalization of this is this language of these cyclotomic Hikita algebras. Okay, so let me discuss the proof first for R equal to 1, since it's easier to formulate things, and then say a couple words in general. Okay, so for R equal to 1, M and R is isomorphic to the Hilbert scheme of endpoints on A2, as we discussed. So our goal is to compare the following algebras. On the left-hand side, we have a equivariant cohomology of the Hilbert scheme with respect to C times. And on the right-hand side, we have these schematic fixed points of M univ 0 and 1. And let us first of all concentrate on the left-hand side, since it's like much more studied, and let me even not to think about the Hilbert scheme here, and think that here we are considering arbitrary Queer variety M of Q. So since I didn't define this variety, for people who don't know the definition, just think about Mn1 or Mn_r, since I defined them. So what is known about the left-hand side, about this equivariant cohomology? So due to Nakajima, McGerdy, and Nevins, it is known that this equivariant cohomology is a free module over the equivariant cohomology of a point. And even more, it's known that these equivariant cohomology are generated by the Chern characters of the tautological bundles on queer varieties. So in our particular case of Mn1, we have only one tautological bundle, which is like V. So we put just a vector space V over the point X, Y, gamma, delta. Any questions about this slide? Okay, great. So we have these 1 and 2, and also what we can do, we can consider the embedding of fixed points with respect to our torus S inside the whole queer variety. And the localization theorem tells us that the pullback homomorphism with respect to this embedding, so it goes from cohomology, from S equivariant cohomology of M of Q to S equivariant cohomology of fixed points, it becomes an isomorphism. So in particular, we see that we have a very nice embedding of our algebra that we want to study inside something very simple. Very simple in the sense that we have an explicit description of it. Yes, equivariant cohomology. So fixed points is just some discrete set, and this cohomology is functions on S to the power number of fixed points. And here certainly I restrict to the case when we have finite number of fixed points on our queer variety with respect to S. But there are many examples such. And in Hikita conjecture, we'll only consider such examples. Okay, and even more. So we have this embedding, and we know where our generators map with respect to this embedding. So our generators just map to Chern characters of the restrictions of our tautological bundles to fixed points, which are just symmetric polynomials on alpha 1, alpha v, where alphas are weights of the action of S on the fibers at fixed points. Let me stop for a minute. So the idea is that our algebra that we want to study is embedded inside something simple in a rather explicit way. So we know where generators go under this embedding. Okay, great. So let me say this even more explicitly in the case of a Hilbert scheme. So for Hilbert scheme, our torus is one-dimensional. So our cohomologies are embedded inside just the C of kappa to the power number of fixed points. And fixed points of Hilbert scheme with respect to C times are parameterized by partitions of n. And this map just sends the Chern class of V to the elementary symmetric polynomial of kappa content, and here we have content 1 of y dot 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 content n of y, and cont is content of the corresponding unit diagram. So this is how the map works. Since this function is symmetric, it's not important in which order we put contents. Any questions? Okay, so let me now explain the idea of the proof. So the idea of the proof is the following. So we have just this. Let me show it again. We have just described certain explicit embedding of left-hand side of Hikita conjecture inside something simple. The idea is just to find the explicit embedding of the right-hand side of Hikita conjecture inside the same algebra and find generators here, which will go to the same elements as generators above Chern classes did.
Vasya, I'm sorry. Can you describe the image of the embedding? I mean, so you get a tuple of polynomials. So is there a way to say what tuples sit in the image?
I mean, this is like generic. So so if you tensor, so if you tensor by the C of kappa, so allow to divide by kappa, then you just get isomorphism. Yeah, so I don't know how to describe the image explicitly. I think. I'm just, yes. So this map is like generically. So generically, if you restrict to generic point, this will be just isomorphism.
I see. Thank you.
Okay. Yes. So the goal is the following: find the embedding, find generators, and that's it. Okay, how to do this? First of all, how to deal with the embedding. Let us recall that our MU universal N1 was resolved by the corresponding smooth symplectic guy, MN1 univ, without zero. And this resolution certainly is C times equivariant. So it induces the embedding at the level of functions on fixed points. Functions on fixed points, these ones, this embeds inside functions on fixed points here. And now the point is that this space is smooth. So fixed points of this space have no interesting scheme structure. That's why these functions are just C of kappa to the power number of fixed points, every fiber. And this is exactly the embedding that we were searching. So it's very natural from this perspective also. On the other words, you just take function here, take its pullback here, and then restrict to fixed points. Any questions about this? Okay, and now how to deal with B part. So to deal with B part,
Vasily, could you please recall what is B?
Yes, sorry, yes. Let me go. So what was our goal? We wanted to construct this embedding, and that we did. And now we want to find generators here such that their images will be the same as the images of Chern classes above.
Thanks.
And okay, so how to find the generators here? It's easy to using results of Lustig on generators on the functions on the whole query variety. It's not so hard to show that these schematic fixed points are actually generated by the coefficients of the characteristic polynomial of yx. So in other words, you have the following function. You map your quadruple x, y, gamma, delta. Here should be 1. To EI of alpha 1, alpha n, where alpha 1 and alpha n are eigenvalues of yx. This is some particular function, and these functions generate the whole schematic fixed points. And then, in order to complete the proof, we need to compute the values of these very particular functions on the fixed points of our family. And let me explain how this computation works. So basically, the observation here is the following. The fiber of this family over any non-zero kappa is the so-called Algebra variety, which parameterizes pairs of matrices such that the rank of a commutator of x and y minus identity is equal to 1, modulo GLN. And there is a very explicit description of fixed points on this Algebra variety, which is due to Wilson. They are still in bijection with partitions. And from this very explicit description, it's easy to see that if we have Young diagram and it corresponds to the pair x, y, then the eigenvalues of yx are precisely the contents of the Young diagram y. And this finishes the proof, since we see the same contents as values. And let me give an example here. So here is the example of n equal to 3. These are, so for n equal to 3, there are 3 partitions, and they have written their contents inside boxes. And then the corresponding fixed points of the Algebra spaces can be described as follows. So you have y, so x is always the same, and y depends on the partition. And when you multiply them, you see that you always get contents. I should also put 0 in books everywhere. Okay, so this finishes the argument for Hilbert scheme. Are there any questions?
So somehow, if I understood correctly, so you were supposed to do some analysis on the singular space, right? On the symmetric power of C2.
Exactly. And
but instead you did complex deformation of it, which made it in the Algebra space.
Yes, yes. And let me say that actually this idea to go this way belongs to Bremerman, Alexander Bremerman. That actually, so the original proof of Hikita, he didn't consider this deformation for Hilbert scheme, for example. And the proof is combinatorial. So he just identified 2 algebras, he found generators and computed multiplication of them. And if you include this deformation, it turns out that everything becomes much more easier to deal with.
Somehow, the idea is that generically, it's very easy to prove everything, because generically, on the left-hand side, you can see the equivariant cohomology, and so we have this equivariant parameters, and generically, everything just is described in terms of fixed points. And on the right-hand side, generically, you have a deformation, and generically, it's smooth. So everything, so this scheme of fixed points is also described in terms of fixed points. So generically, just need to establish a bijection between sets of fixed points. But then you have to sort of do something to check what happens when these parameters become non-generic. And this is somehow the, and there you already need to work with a singular space and so on.
Okay, great. So let me, I have 10 minutes, yes? Okay, so let me then briefly say what to do for arbitrary R. Actually, the proof is very similar. And then I will say something about certain general conjectures. So let's say 5 minutes to arbitrary R. So in general, we want to compare.
Vasily, you can be not so modest. If you go beyond 10 minutes, it's okay.
Okay, so I'll be slower. Actually, I don't have so much to say. Yeah, so I hope that I will do for 15 minutes. Okay, great. So now R is any, and we want to compare this algebra, cohomologies of M and R, with the functions on this center specter of schematic fixed points on the center of rational Cheritenic algebra. So on the left-hand side, the picture is the same as we discussed. So we have equivariant cohomologies. They are embedded inside fixed points, equivariant cohomologies of fixed points, which are just functions on our torus to the power. And now we take a power and number of multi-partitions are multi-partitions of n, because fixed points of S here are parameterized by R multi-partitions of n. And still Ci of V maps to very explicit elements here. So you can call them like shifted multi-contents of Young diagrams. Just characters of tangents fibers of our V. Okay, and what about right-hand side? So as always, we want to embed this algebra inside this and find explicit generators. And the easiest way to do this is to use the representation theory of the rational Cheritenic algebra. How to do this? First of all, let me recall that our rational Cheritenic algebra is generated by excess bias and by the group gamma, which is the semi-direct product. And the action, C times action, with respect to which we're taking schematic fixed points, corresponds to the grading on this algebra, such that the degree of xi is 1, degree of yi is -1, and degree of gamma is just 0. And schematic fixed points, which we are considering, just from the definition, they are the quotient of this center by the functions fi, which have non-zero degree. Great. And let me now recall.
I said, if you go to center, then you've got like only positive gradings?
No, not necessarily. Note that if you have only positive gradings, then the schematic fixed points are not interesting. Yes, you just have. So yeah, so you have both gradings.
Symmetric functions of axis, I think something like this should be in the center, and symmetric functions of y's.
Yes.
So some
At least
elements of
some
degree
R.
0
powers
also
of x to the r.
Yes, we may have many elements of degree 0. Yes, we will talk about them soon. For example, these Dangle-Obdam elements that are certain deformations of yi times xi. Okay, so and reducible representations of gamma. This is like the first sign that we're doing the right thing. The reducible representations of gamma, they are in bijection with the same set of R multipartitions of n. And then starting from R multipartition, we can consider the corresponding irreducible representation of gamma. And then using this general procedure, we can associate to it the induced like standard or Verma module for the rational Cheritenic algebra and consider its simple quotient that I denote by L of lambda. So this will be a simple module over H and R. And you can think about it as about a reducible representation with highest weight S of lambda. Okay, and then the center acts on this L of lambda by some scalars. And since the center in particular acts on the highest component of this L of lambda, it's easy to see that this action factors through the action of our Q and R. So the elements of non-zero degree act by zero. So we have a map then from Q and R to the direct sum through all lambda of endomorphisms over H and R of this L of lambda, just by acting on the corresponding representation. And this direct sum is exactly the algebra inside which we wanted to embed our schematic fixed points. So we get the desired embedding using representation theory. And the last ingredient is to find the good generators of this algebra. And the generators are actually symmetric functions on U1, UN, where UIs are so-called Dunkel-Obdom elements of the Cheritenic algebra. And these Dunkel-Obdom elements, they look as follows. You have 1 divided by R, YI, XI, plus some Jusis-Murphy element, plus something that depends only on this Z mod RZ to the power n. And it turns out that these this Q and R consists of symmetric functions on this Dunkel-Obdom element. Great. So we have generators, we have embedding. It remains to compute the image of these generators. But the generators are more or less Jusis-Murphy elements. And we act by these Jusis-Murphy elements on highest weight component of L of lambda, which is S of lambda. And we do know that they act just by contents. So we see that the image of these EIs of Dunkel-Obdoms coincide with the images of Ci of V. Or since both of them are these shifted multi-contents of Young diagram. I believe that from this description, it's easy to believe that you get something very similar to the content, slightly shifted. Okay, so any questions about this proof in general? Okay, and let me then finish with generalizations and conjectures. So in principle, we can start from arbitrary equivariety M of Q. Then the symplectically dual side will be this so-called this M of Q, so-called Coulomb branch, which was mathematically defined by Breyerman, Finkelberg, Nakajima as a spectrum of a certain equivariant Borel-Moore homology of some variety of triples R. I'm not giving definitions. And the universal deformation of this M of Q is also has the similar description. You just need to make your group with respect to which you take equivariant homology larger. You should multiply by your torus S and take equivariant homology of the same space R. So Hikita-Nakajima conjecture in this case compares cohomology of M of Q equivariant and schematic fixed points on this algebra. And on the left-hand side, we do have generators, which are Chern classes of tautological vector bundles. The point is that the right-hand side also has very natural generators. And the fact that they are generators follows from the work, from the results of Finkelberg, Sympletic, Weeks, Kamnitzer, Webster, and Jacobi. And let me explain these generators. you can do what? You can consider just the trivial vector bundle on your variety of triples, Vj times R, but consider it with an interesting equivariant structure. So the equivariant structure will be induced from the action of GV on Vj, which comes from the projection. And you can consider these bundles as like tautological vector bundles on R mod your group with respect to the equivariant homology. And then the claim is that Chern characters of this EJ do generate the algebra of schematic fixed points. This is known in general. And this follows from the results of people that I mentioned. Then the claim that you can check that in our particular case, when you are dealing with ADHM space, the isomorphism that we have, it actually identifies these two sets of generators. So it maps Chern characters of Vj to Chern characters of Ej. And the conjecture then can be reformulated in the following more precise form. There exists, in this particular case of quiver varieties, that we have isomorphisms between these algebras that maps this generator to this generator. And let me then finish with just saying that basically then the Hikita conjecture, so to prove this conjecture, it's equivalent to do the following thing, which is certainly complicated in general. So you can consider Ci of Ej as a function on M universal of Q. Then you need to show that values of these functions on fixed points of our universal deformation is the same as the characters of the tautological bundles on quiver varieties at fixed points. So that's what I meant, but maybe this is not about these beta roots, and this is a different thing. So from yes, but this is some statement about some like numerical invariants to coincide. One numerical invariant is a certain value of certain functions on a fixed points, and another numerical value on the dual side is the character of the fiber of certain bundle.
But beta roots are the Chern roots of the tautological bundles, actually.
Yes. That's why I thought that this may be related. Yes.
Just that maybe you need some quantum deformation, quantum in sense of quantum cohomology, to make this. But it looks from the way you proved, you didn't need anything. You didn't need to go beyond, the ordinary geometry. So, in fact, it looks like the proof was just a twistor rotation. You just compared. You looked at this variety in different complex structures and compared the structure of fixed points in the examples you gave. So
yes, but
if it can be done really elementary. So
yes, but if I understand correctly, so actually, these fixed points on Coulomb branches, they are really hard to describe in general. So, and even in this case of ADHM space on the dual side, we used representation theory in order to simplify the arguments. So you can also do precisely the same proof as for Hilbert scheme with computing values of certain functions on fixed points, but it will be much more combinatorially involved, actually. Okay, so that's it. Thank you very much.
Okay, thank you.
Thank you, Vasya. Maybe there are other questions.
To make things more interesting, so can you go beyond quiver varieties? So can you, for example, look at the, let's say, Calagier-Moser space for the, elliptic curve? So take the Hitchin space.
So I haven't tried yet, so I don't know. Maybe Alexander has a comment.
No, I don't know. I mean, in the case when we're not dealing with defined varieties, I don't know any sensible statement.
Okay.
Maybe let me make a comment here about one detail that I haven't discussed, but that is really like important, and you also need to prove this. It's the following fact. So at the level of pure varieties, we do know that these equivariant cohomologies, they are a free module over equivariant cohomologies of a point. And this is like the first starting point. Without knowing this, we cannot construct embedding that we want to. And at the level of at the dual side, the claim is that schematic fixed points of the universal deformation are flat over the base. And so it's not so, there's no way to prove this in general. So so Ben Webster told us that he knows the way how to prove this in this particular setting that I'm talking about for these Coulomb branches. But when you go beyond Coulomb branches, even this question arises from which you should start to do. General.
I have a question, maybe it's for Nikita. Nikita, is there any theory in which spin generalization of Calogero-Moser plays a role?
That's what he was talking about. This is the high rank case. So M and R space is this. If you take the deformation of the singular space, not the resolution, but the deformation. So just like in the rank 1 case, when you subtract 1 from commutator xy. So so for the high rank case, that's precisely the spin Calogero-Moser space. When spins have dimension R, the spin variables. But it's a rational case, so it's a rational spin Calogero-Moser.
I understand this. Elliptic is much harder, should be, to some extent.
I mean, there is some relation between. So this analysis of the eigenvalues of the function yx, which was done, there's a map from the rational Calogero-Moser to the trigonometric one when you map the but in the rational case you consider you add the oscillator potential, which I think is this yx term, and so this analysis probably can be also generalized to trigonometric case, but elliptic, yes, it's hard.
Yes, actually this is maybe let me show then you. I forgot to show generalization. Maybe this is related. So in principle, what you can do, you can replace equivariant homology by equivariant K-theory. And you can also replace equivariant homology by still equivariant homology, but with respect to the S times C times, and still do this for M and R. So, and in some sense, it's replacement on the dual side corresponds to passing from rational situation to the trigonometric situation of homology by K-theory. Yeah, sorry.
Thank you. More questions? Thanks for.
Yeah, can you say again? When you replace left-hand side by K-theory, what do you do on the right-hand side?
Yes, so let us look at in this form when you already deal with quiver varieties. Mm-hmm. So on the left-hand side, you put K-theory, but on the right-hand side, in the very definition of Coulomb branch, you are considering equivariant Borel-Moore homology of some space R. Mm-hmm. You can replace this H by K.
Okay. So you're doing K-theory on both sides?
Yes. And this still should be true. So yeah, and I believe that this case that we considered with Pavel for K-theory, so Pavel Leitengov explained me that this should be easy, and Alexander Breman also. So this should be doable. just to directly generalize everything from A cohomology to K theory.
Well, I don't know how easy it is because this might be my ignorance, but for example, for the Hilbert scheme, if you consider the equivariant K theory of the Hilbert scheme, I don't know any good algebraic description of it. I don't know.
I see. Yes.
I don't know if any. It's actually interesting because somehow it should be an algebra of Laurent polynomials in U, which should be non-semi-simple when Q is a root of unity of order less or equal than n, something like this.
But still,
I don't know exactly how to describe it algebraically.
But still, we do know that we have generators which correspond to Chern classes, yes, and that this algebra is free over the base, yes.
Yes, but somehow just anyhow. So
I believe that we actually don't need to have an explicit description of the algebra in order for this approach to work. You just embed, and there you embed using representation theory of this trigonometric version of using the center of the algebra that you described in your paper with Ettinghoff and Finkelberg, and using representation theory. But yeah, this is just my hope.
Maybe, but okay, I don't know.
Okay, thank you.
Could I also ask a question?
Yeah, sure.
What if we consider instead of space M and R, the fixed point set of discrete group action, which multiply X by root of unity and gamma and I forgot your notation. Gamma and delta also multiply by diagonal matrices of root of unities.
Yes, so I believe that this
basically turns into a fine Lamont space. Whether you could construct something like symplectic dual for it, or how this construction will be modified, or it's really not possible because such kind of this action really doesn't preserve symplectic form.
So you are considering not the action like, so I mean that if you consider the action as like eta inverse, where eta is a root of unity of order R, then the fixed points will be this space.
Yeah, but then you're saying we basically get quiver variety again, and then therefore you know how to deal with it. But if we consider non-symmetric action which does not preserve,
I see. I don't know if there is. I don't know if there is if there should or exists a symplectic dual to such variety.
Okay.
I mean, it doesn't preserve symplectic structure, yes. So fixed points are not Poisson, yes. So maybe it's not in this picture.
And also, how this answer would look like for more simple quivers, like just T-star to Grassmannians, where this beta roots would be just beta roots of usual spin chains. What will be on the right-hand side?
Yes, so as you have seen, even when you take T-star to Pn-1, you get something interesting on the dual side. Yes, you have this resolution of A2 factor by quotient by Z mod and Z. Yes, so in general, you can describe it using realization of all of them as, for example, as Slodevy slices and resolutions of Slodevy slices, or as quiver varieties of type A.
Okay.
Yeah, so maybe just as I said in the comment, I think in the case when you have T star G mod P, you can there's this theorem by de Concini and Procesi, at the beginning, they were for cohomology of Springer fibers are described as fixed points in the closure of some nilpotent cone. And I think Hikita also generalized it to the dual side, where you describe cohomology of partial flags as like fixed points in the like Slodoid slice intersection with the nilpotent cone.
Yes, thank you very much for this.
Yes, but it's only type A.
Type A.
So
Yes.
this actually falls into this realm.
There is some generalization of this result, I think, in the literature, where you need to put some condition that the nilpotent element has to be distinguished in a parabolic on one side and distinguished in like regular in Levy on the other side.
I see. And could you please send me a reference to the place where it's proved not for type A, for Gmod P, because I haven't found any reference.
Okay, yeah.
Thank you very
In
much.
principle, it's also proven for all equivarieties of finite type. But well, in fact, almost. I mean, it's proven modulo some technical points. There's this work of Damnitzer and I don't remember who else, where essentially they prove well, basically modulo some technical thing on this dual side of the singular variety, they actually proved it. But,
yes, and actually, if you look at their isomorphism, you will see that this still holds.
yes, sure.
And so for K theory, which you this generalization which you briefly mentioned, this rational Cheritenic algebra will be replaced by what? Actual trigonometric Cheritenic algebra in this example, or what will happen?
Yes, I think so. Certain version, yes.
Yeah, because okay.
Yes, in the Gilbert scheme case, yes, and
Yeah, just it was hard for me to follow everything. So this Cheritenic algebra, it has something to do with those with the fact that fixed points of Mn1 are related basically in correspondence to Macdonald polynomials. Is it like the same type of statement that that if we take the spherical subalgebra of double affine Hecke algebra, it will be it will be some sort of in the end infinite limit, some sort of controlled algebra which which is related to Macdonald polynomials. Is it the same type of correspondence here? I mean, not correspondence here. Is it the same double affine Hecke algebra, or it's different one? I'm just confused.
Let me just say that yes, I think that there is only one rational Cheritenic algebra that appears in the Hilbert scheme picture, and such that functions on Hilbert scheme as a spherical subalgebra inside it. And yeah, that's all what I can. Yeah, I don't know. Maybe we can discuss this in privately.
Okay, I see. No, I said, yeah, I couldn't really formulate the question correctly. Yeah.
Sorry, can I ask a last? Yeah, can I ask another question? I'm just confused. By this model, what do you expect to be the symplectic dual of this MRN?
Sorry, sorry. Could you please repeat?
Yeah, so you have computed the cohomology. Yeah, you discussed Hikita conjecture for cohomology of this key-circle space.
Mm-hmm.
And so, what is the resolution on the dual side?
Okay, great. So let me draw it. Maybe the most explicit way how to do this is, so actually, so I discussed this, so M and R, that this guy is dual to this Sn of A2 mod ZR2.
Mm.
Yes, but actually, this space has also, and this is something special about the ADHM space, this space also has a realization as a equivariety. So this is a equivariety like M0 corresponding to the following quiver. You have a cycle, you put N everywhere, you have R vertices, and you have one-dimensional framing.
Mm-hmm.
And then you can resolve it by the corresponding quiver variety. So here you have M0 and you can put the same, but without zero.
Okay.
But you can also do this in terms of column branches using GIT quotients.
Yeah, okay. Okay, just want to make sure. Okay, thank you.
I'm sorry, what's the dimension of this variety, the last one?
Yes, yes, that's a very, very good question. So note that when we are, so here the dimension is 2nr, and here the dimension is 2n.
Mm-hmm.
Yes, so it does not depend on r.
Mm-hmm. Mm-hmm. And this M0 of this cycle is what? So
is the same. It's they equal.
This arrow just means that's the same. Yeah. Okay.
Yes. Yes. Yes.
But is it clear that it does not depend on R?
From the Coulomb branch perspective,
yeah,
it is clear. Yes. If you construct, yes, for Coulomb branches always generically just like T star of a torus modular Weyl group, and torus is always the same, independently on the framing that you put and dimension that.
Thank you.
Okay, maybe we have sufficiently many questions. Thank you, Vasya, very much.
Thank you very much for the invitation.